Got it. Okay, so next gonna ask again if anybody has any questions from what we've been doing so far. Okay, so the plan for today is I want to talk about a little bit about structures of rank 1, just to play around with the examples of rank 1 and see. I don't know, just look at a few things in that particular case very shortly, but just to give an idea to see how that works for intuition. If you guys read, for the ones who looked at the first part of the book, there's a whole chapter on atomic structures, existentially atomic structures. I'll repeat the stuff from there. Then I want to go back and talk about the equivalence between the orbit rank and the Scott sentence rank that we mentioned before. We already proved one direction. I can repeat that. And then we'll prove the other direction. To prove that, there is a type omitting lemma that is necessary. I was thinking to skip the proof, but I guess we can decide when we get there. I mean, I can give you the ideas how to use it and everything. The proof of type omitting lemma might be, I don't know, long, and maybe it's better to just look at other things instead, so that we can see more things in the next. And then after that, go into back and forth relations, which I also promised the first class. Okay, so let's start with existentially atomic structures. Okay, so we say definition. So structure A is a structure, is atomic. If for every tuple A in A to the less than omega, less than n, that's what I'm using. There is an existential formula finitary such that, which defines the orbit of A, such that the orbit of A in A is definable by this formula. Such that A models phi A. Okay, so existentially atomic is it's kind of the simplest class. I want to just talk a little bit about this kind of simplest, well, not the simplest class. The class of the simplest structures are the existentially atomic. Every automorphism orbit is definable by a finitary existential formula. So finitary, I mean just the standard first order logic without infinite. And E formula or existential formula is one that has existential and then quantifier free. Okay, so an E formula is one of the form there exists x1, there exists x2, there exists xk, such that psi k, where this one is quantifier free. And finite type. So that's an existential formula, very simple formula. Okay, so this is kind of every isomorphism orbit is E definable. So I guess the first, well, then I guess another definition I'll use it. So maybe I just write it down. So A is E atomic over parameters. If it's existentially atomic over parameter, essentially. If there is a tuple P bar in A, such that the structure that you get by adding to A constants, naming like those elements. So you add this tuple to the structure and you name them with constants, is E atomic. Okay, that's what it means over parameters. If you fix some parameters, then the structure becomes existentially atomic. And that's the same thing as saying that these formulas over here feeds of A. Okay, let me put a name here. This finite existential formula. Phase of A that depends on A. So there's those formulas used essentially are allowed to use parameters P. That's what that means. Okay. Cool. So observation, existentially atomic structures have rank 1. Have orbit rank 1, which is the least possible. I mean, in our definitions, that was the least possible. Let me see what the definition was. The orbit rank of a structure, if you guys remember, is the least alpha greater than 1, such that every isomorphism orbit is sigma alpha definable. In this case, they are all sigma 1 definable. They are existentially atomic. So they are all existentially definable. All the isomorphism orbits are existentially definable. And in particular, they are sigma 1 definable. So that means the least alpha is as 1. Okay. So these are the lowest Scott rank possible are these guys. And I guess we can also observe the converse of these, which requires a little observation. And vice versa. If the orbit rank of A equals 1, then A is E atomic. And what's the reason for this? Let me just tell you what the reason is. So the orbit rank, this means that all isomorphism orbits are infinitary sigma 1 definable. Right, so that means that these formulas that we have up here for each tuple A, we know they are sigma 1. Okay, but if you have a sigma 1 formula, so these formulas phi sub A of X are of the form infinitary disjunction for I in the natural numbers of an existential formula. That exists Y such that psi A, sorry, X, Y. And this one is quantifier free. Right? So each orbit can be defined by something of this form. Okay, but if this formula that is defined in the orbit of A, well, it's true of A, and if it's true of A, one of these guys must be true of A, right? Because the whole disjunction is true of A. If this disjunction is true of A, then one of them must be true of A, right? And if you just restrict yourself to one of the guys, to one of these guys, to the one that is true of A, we are getting a stronger formula because we're going from a disjunction of a bunch of things to just one of them. So you get a stronger formula that is true of A. If it's true of A, it's true of everybody that is automorphic to A. And it's stronger than this one that was true of nobody else. So the one formula, the one of these formulas that is true of A must also define the orbit of A. So if you have an infinitary disjunction defining an orbit, then one of the disjuncts must define the orbit too. That's what I'm saying. Whichever of the disjuncts is true about any element in the orbit. So that means that every orbit is existentially definable. So these are all existentially definable. So that's why you get that the structure is existentially atomic. Cool. Great. So yeah, so this with the line above, we get that this implication is the same. So existentially atomic is the same as rank 1. Another observation, existentially, for the ones that know, well, probably all know what atomic means in model theory, right? So the structure is atomic in model theory if every first of the type is principal, or that's how you say it. So that's the same as saying that every orbit is equivalent. Actually, you can prove it. That's equivalent to saying that every orbit, automorphism orbit, is definable by a first order formula. That's in the model theory. So this is a strengthening. So it's not that just every orbit is definable by a first order formula, it's that the formula is also of this form existential. So this is very similar to the notion of atomic from model theory, except that now we have this stronger requirement that the formulas are existential. And these are the ones of Scott rank 1. Good. So let me mention a few examples. Well, okay, so the rationals with less than or equal, we mentioned this before. Well, we mentioned it for rank. Is the only linear ordering that is E atomic. The proof of this, you can look it up in the textbook in part 1. It's half a page. It requires a little trick. The thing is a good exercise if you guys want to try it, but I have more exercises for you here. But that will be one. showing that Q is existentially atomic is very easy, but that is the unique one is a tricky one. But okay, I'll leave it at that, just to leave you the example. So another simple, linear orderings are always very simple. That's why I mentioned them in this case. So, so consider adjacency linear ordering. So I'm gonna just define what it is. Adjacency. Of J. Linear order. Which we are gonna is gonna be of the form L less than or equal to a domain L, an ordering, and an adjacency relation. So it has an ordering and it has an extra relationship. And then where this adjacency, that's what I call an adjacency relation. It has the extra relationship for adjacency. Adjacency means that the two elements are next to each other, are adjacent. So this means X less than Y, and there is nothing in between. And there is no Z with X less than Z. My iPad is getting slower. That's what adjacency means. The 2 points are adjacent, next to each other. I see a question in the chat, I guess. Do we presume A is countable here? I don't know where, but yes. In the definition of existentially atomic, I always presume A is countable, but again, doesn't need to be countable. No, so it works in the uncountable case too. Not everything I say is going to work in that case, but yes, for so far, that's good. Okay, so an adjacency linear ordering is existentially atomic over parameters if and only if you can write L as in this form where each is of I is one of these 0, omega, the reverse ordering of omega, omega going back, omega plus omega star. So this is two linear orderings converging to each other, omegas, or or something of the form M times Q, where M is a finite number. So you have M things and densely many of these intervals that have exactly M things. This is in the natural numbers. So that's just to show you what these things look like. The proof of this, it's a bit hard, showing that those guys are atomic over parameters is not hard again, and you can try it out. Showing they are the only ones, it requires some work. But then, okay, so then you see that these are the only ones. And actually, these are also, if you remove the adjacency, these are also the only ones of Scott rank 2 over parameters. So that when you add the adjacency, it's kind of like going one level up in the Scott rank. I'm not going deeper into that. That's another part of the book. But ion relationship is one more quantifier and it's complete. So these are exactly the ones of Scott rank 2 with parameters. You can characterize them as these guys. Somebody was asking how many are there, how many orderings are there of Scott rank 2, I think Young. And with parameters are exactly these guys. So countably many.
Yes, I asked this question.
Right. For Scott rank 3 blows up, then let's continue many, and you can't characterize them anymore in such a nice way. Okay, some more examples. So finite. No. So fields that are algebraic over the prime subfield are existentially atomic. Connected graphs are existentially atomic using one parameter. You need a parameter. Abelian torsion-free groups of finite rank are also existentially atomic over parameters. So there are a bunch of things. So these last three follow from a lemma that I'm not going to prove. I could if you want any of these things next time. That if a structure A is existentially algebraic, then it's existentially atomic. Existentially algebraic is the same as when in model theory, when you define algebraic. Model theory, when you define algebraic, you're saying that for every element is a formula true about it, and that is only true about finitely many other elements. So it's the same, but for existential formulas. So up to this here is for every A, there is a formula psi x such that A models psi, and the number of things that model psi is finite. So there are only finitely many things that make it true. So A might not be definable. If every element is definable, then of course you're existentially atomic, because it's existentially definable, then you're existentially atomic, because you not only define the orbit, but you define the element itself. But in this case, you're not definable, but close. There is an existential formula that defines you up to finitely much. So that's existentially algebraic, and these guys are all existentially algebraic. So for instance, if a field is algebraic, the algebraic word there, that's where this comes from. If a field is algebraic, if every element is, I'm gonna put you guys up here so I don't end up looking up. If every element, sorry, I'm getting there. So I see you. So algebraic means every element is a root of a polynomial. Every polynomial has only finitely many roots, and being a root of a polynomial is an existential formula. Actually, it's a quantifier-free formula. So for every element, there is a formula that defines it up to finitely many other elements, and those are existentially atomic. That requires a proof. Actually, it's a pretty nice proof. But okay, I'll leave that for well, for you guys to read if you want, or if you want a topic for next time. Okay. Okay, so let me continue with existentially atomic formulas, and how they relate to this computability notion of computable categoricity. So definition, we say that A is effectively E atomic. If the family of formulas are defining the orbits, can be taken to be computably enumerable. If the set C sub A of formulas, the ones that define the orbits of all these elements, can be taken to be CE. Okay, so if you can define a computably CE meaning computably enumerable, no? So if you can find, I mean, for every tuple there is a existential formula that defines its orbit. There are maybe many, not just one. If there's a way to define this set of formulas that define all the orbits in a computably enumerable way, we say that the structure is effectively existentially atomic. Okay, so we're adding the property that we can computably enumerate all these definitions. And the theorem, and that is due to Vensov, Goncharov, Netrasin, these people in Russia, but they didn't use this notation, but they kind of were doing these things. So there are two theorems I'm going to mention. So I'm going to say A is effectively E atomic over parameters if and only if A is what is called computably categorical. So let's start assuming that A is a computable structure. And what it means to be computably categorical, this means that relatively. This means that for every copy B, for every copy B of A, there is a computable isomorphism from B to A. So this is an interesting theorem because this notion of relatively computable categorical is studied quite a bit in computability. Okay, so this is not correct, completely correct. Let me fix this. And isomorphism computable in B. Right. So if I give you a new structure B, but I know if I give you a structure B that I know is isomorphic to A, how hard is it to find the isomorphism? Well, in this case, the structure is relatively computable categorical. It's just using B as an oracle. I can figure it out. the isomorphism. Okay, so that's what that says. So I mean, the structure, if the structure B is non-computable, it's going to be very hard to find a computable isomorphism between B and A, which is what I wrote before. So, but at least in this case, we can find some the isomorphism computably in B. Okay, so this is pretty strong from a computability viewpoint because it tells you that, for instance, if we restrict ourselves to computable copies of a structure, one thing that could happen is that different computable copies of the same structure, it happens a lot in computable structure theory, different computable copies don't have the same computability properties. Like they are isomorphic, but I don't know, certain relation here is computable and here is not, certain function here is computable and here is not. This can happen a lot. And so that means you have to be studying the different presentations of copies of a structure to see what properties are in common, etc. When a structure is computably categorical, it means that whenever you have two computable isomorphic copies, there is a computable isomorphism between them. So every property that you have in one side, you have in the other side because you have this computable isomorphism, and you can translate the properties from one side to the other. So these particular kind of structures are particularly nice from a computability viewpoint, because essentially up to computable isomorphism, they have only one representation. So that's why the name computably categorical, because it's kind of one up to computable isomorphism, it's only one representation. Okay, so this theorem is very hard to prove in one of the directions. I mean, let me prove the easy direction, and I might give you, I was thinking today I could prove the other direction next class if you want to go into the topology of the space of structures related to this. But let's do just the easy direction, which is this direction. So suppose that A is effectively existentially atomic. Now we want to show, and then so consider. So let's write the assumption. So A is effectively atomic, and let's take B belongs to copies of A. So A, in other words, B is isomorphic to A. And now we want to find a computable isomorphism, an isomorphism between B and A that is computable in B. That's what we want. And how are we going to do this? Well, so here we put B, and here is A. Okay, let me, just to simplify a little bit, let me forget about the parameters for now. Let's assume that it's essentially atomic. If there are parameters named with constants, we can just map from one side to the other, start with mapping the parameters. That's pretty easy. Let's, just to simplify, suppose there is no parameters. So we want to define a map from here to there. So what we're going to do is a back and forth construction. So we start taking an element here, and now we're going to try to find one here that matches it, and then we're going to extend this one here, and we're going to find one here that matches it, and then we pick one here, and we choose here that matches it, and we want to do it in a way that we end up going through all of A and all of B to make it by a bijection, and we want to make it in a way such that they satisfy all the same atomic formulas. So it's not only a bijection, but an isomorphism, right? And to do this, so step by step, we guarantee that Okay, so let's put a name to this family. Let's call it S. S is the family of all the computer numerical family of all these formulas that define orbits. Guarantee that there is formula psi of X that belongs to the family S, such that psi such that B models psi of B0 up to BS, and A models psi A0 up to AS. So we're going to choose a different one at every step. So this is step S. Okay, so at every moment, we want to make sure that when we define the first S many up to here, this tuple of elements and this tuple of elements satisfy the same formula from the family S. Essentially, that means that they are isomorphic, right? Because these formulas are defining the orbits of the tuples. So if two tuples satisfy the same formula, that means they are automorphic if in the same structure. If they are in different structures, these are the same structure. They are isomorphic. So that means they are isomorphic, right? So if you satisfy the same formula from the family, you're isomorphic. So that means you're in track. You're going in the right direction. So you want to do this back and forth process of choosing from one side and the other, so that at every step there is some formula in your family that is true about both.
Antonio, do you need the definition to be uniform in CE? I mean, let's say uniform way to enumerate all the types.
A uniformly CE, you're saying?
Yeah, I mean, what's the effect? What's the definition of effective extension atomic? Is for every A, the type of X is CE?
No. I don't mean the type of A. Maybe I should write that a bit better.
No.
So this is the family of all the formulas that define. These are these formulas.
Okay.
So for every A, we have a formula that defines the orbit of A.
Okay.
So those are the formulas.
I see.
So maybe let's write. Maybe let me write down that what that S is in. I don't have a space here. Let me write it here. So I want to write what. So the word we usually say that says S is a Scott family for A if S is a family of functions such that two things, if psi of X for every formula in the family belongs to S, and A models that this formula is true in one tuple and is true in another tuple, then these tuples are automorphic. And for every A in A, there is formula psi in S such that A models psi of A. So it's essentially a Scott family is a set of all formulas that define the orbits of the elements of the structure. So that's the purpose. That's what I want, and then so that's what this one is. So this is a set of all the formulas that define all the orbits. So that's a Scott family. So what I'm saying by here, what I'm saying, effectively atomic means that there exists a set S with those properties that is CE. Okay. So when we're doing this construction, right, we're guaranteeing that at every step, the things on the left satisfy the formula and the things on the right satisfy the same formula at every point, which guarantees that they are isomorphic so far. And to do this, so what do we need to do the back and forth? So suppose we have defined, I don't know, the first few many, and now we want to we choose a B2 and we want to find an A2 that matches it in the sense that they satisfy the same formula. Well, what do? We have this up to here. We look for some formula in S that makes it true. S is computably enumerable, and the formulas are existential. So we can enumerate S, and we can check if it's true. I mean, checking an existential formula is also computably enumerable. You have to wait until you see the witnesses, but it's also computably enumerable. I'm going through a few details quickly here. So you can wait until you find some formula in psi in S, and that you see, you can verify that it's true because you see all the witnesses. And when you do that, now you start looking for some A2 in A that satisfies that formula, and that's also something that is CE. And when you do, then you map them. So you can do this computably. Cool. Cool. So, and about the uniformness, I mean, if you're not using parameters, this construction is completely uniform. There was no step in which is uniform. So actually, we are building this isomorphism straight from the structure B right away. Where does it come up that is computable in B? Well, it comes up because we need to verify B satisfies these existential formulas. So there we need to know how to calculate the relations in B. So that's where we use computable in B. Okay, so I mentioned that maybe I think a next class will do a proof of the reversal, but that's a bit tricky in the uniform case. That is a bit simpler. Okay, another thing to mention here, which is what I mentioned the first class, if you remove this notion of effectiveness, then you're going to get computable in some oracle, because there is always a Scott family, a family like S of formulas, if you're existentially atomic. So it might not be computably enumerable, but it's going to be computable enumerable relative to some oracle. So that means you're going to get this theorem relative to that oracle. And then one observation that we can make also next time is that computable relative to an oracle is the same as continuous. Every continuous function is computable relative to some oracle. So a version of this theorem is true if you remove effective from here, and if instead of computable here you replace it by continuous. Okay, and it needs to, a version of this. We'll can go into this next time when we talk about the topology of the space. Okay, so that was a sketchy proof. Any questions? There is some way to clarify something.
Do we need also the isomorphism also to be computable in B joint A or just in B?
Oh, okay, so yeah, so here I'm assuming A is computable.
Oh, okay.
Just to simplify that part.
Thank you.
If you didn't assume that, then yes. Cool. Okay, so the atomic structures are kind of quite interesting from a computability viewpoint, and they are the ones that have Scott rank 1. What we're looking at. General Scott rank. I think just to keep things simple, we come back to these guys. What's the time? Okay, very good. So let's see where we were last time, and let me tell you how is that you will prove the reversal. Where were we last time? Okay. So here's a theorem that says that the Scott sentence rank of A is less than or equal orbit rank of A. We showed that last time, and essentially, and the way we showed it is that if you're given the Scott family, so if every orbit is sigma alpha definable, that's what it means to have Scott rank less than or equal alpha. If every orbit is sigma alpha definable, then we can find the pi alpha plus 1 Scott sentence. That's what it means to have Scott rank less than or equal alpha. Right, that was the definition, right? The definition of orbit rank less than or equal alpha is that we have every orbit is sigma alpha definable. Scott sentence rank less than or equal alpha is the same thing as saying that you have a pi alpha plus 1 Scott sentence. And a Scott sentence was a sentence that is true about A and about no other countable structure. And we did that by showing that given these formulas that define all the orbits, we can write down a Scott sentence for A of this complexity. And we can write down the one from the proof, the one that we got when we prove that formulas that structures have Scott sentences. That one had that complexity. All we did was counting the quantifiers. And that was, here is a picture of when we counted the quantifiers last class. Let's not go through that again. Now we want to prove the other inequality. So let me copy this. So now we're going to call this a theorem. I think I need to reinitialize my iPad because it's becoming slow. When we take the break a loop. The theorem is not that we got the other direction. And therefore that they are equal. So to prove that theorem, we're going to need the type omitting lemma, which, as I was saying, I'm inclining to not to skip the proof. I can tell you a little bit about the proof, but as you guys want. So okay, so I need a definition first. So type phi x is a, what is a type? Let me write it down and then we define the notions. Is I'm going to define this, what it means to be sigma alpha supported in a structure A if there is a sigma alpha formula, let's call it phi of x, such that, well, first A models that there exists an element that makes it true. That's kind of obvious, it's trivial. And phi implies all the formulas in the type. And A models that for every x, if phi of x holds, then all the formulas in the type are true. By a type here, I just mean set. So by a type, set of formulas on free variables But so if people are familiar with types, that's all they are. It's a set of formulas on these variables. Richie, everybody's good with types from model theory?
I think so. And the definition you provided is clear.
Cool. It's just a set of formulas on these variables. And we say that this set of formulas is sigma alpha supported if there is sigma alpha formula that implies them all. And that is realized by some element. And this is sigma supported within this structure. So that means in the structure it implies them all. So it's similar, but not the same, to the idea of like a principal types in model theory. In model theory, principal type is a type such that there is a single formula that implies all the ones in the type. And usually this formula, if you're talking about a complete type, this formula belongs to the type. So it's like from all the formulas in the type, there is one that implies all the other ones. So you don't need infinitely many formulas, you just need one, essentially. So
do we need arrows to be left and right arrow?
So here we only have one implication, right? So in the case of model theory in principal types, we have the if and only if right here. When you talk about the principal type in model theory, you have an if and only if. In this case, no, it's just one direction. And then these are, by the way, these are what I'm calling type, but sometimes in model theory they're called partial types. They don't contain, and a complete type contains for every formula either it or the negation. That's not the case here. So it's just some set of formulas. And yes, no, the formula phi does not need to be part of the type in this case. Supported is kind of a weakening of principle. Just it generates exactly the type, but it implies everybody in the type. And the type omitting lemma this is a version of the type omitting lemma. I guess this precise version, I guess it's in the book. I don't know if it's anywhere else. There are many versions for type omitting lemmas for infinitary logic. And none of them is exactly the one I need. So this is the one we need here. This is a bit more refined than the more common versions. It's more refined in the sense that it's more careful about the alternation of quantifiers of everything than the other versions where they didn't care about that. Okay, so what is the lemma say? So let A be a structure.
Oh, we have a question in the chat box.
Go. Oh yes, Sulin, yes, thank you. These formulas, and in this case, we're talking about formulas, infinitary formulas. So L omega 1 omega. So yeah. Let me write that down. In L omega 1 omega. So yes. By the way, just mentioning about the question. So these formulas are called first order because the quantifiers are over elements. They're just infinitary first order formulas, the ones in L omega 1. So we allow infinitary formulas here. So yes, thank you, Sulin, for the question. So let A be a structure and phi be a by alpha plus 1. I'm gonna omit the in on top because that's all we care about. It's always in on top. So infinitary by alpha plus 1 sentence true of A. So let phi of X be a partial type. So all the types of partial type of pi alpha formulas. So we only assume this is a set of pi alpha formulas, but not more. That is not sigma alpha supported. So the set of this type is all the formulas are pi alpha, and there is no sigma alpha formula that implies them all. Then we can omit the type. So that means we can find a model of this formula that omits the type. Then there is a structure B. A structure B that models phi and omits phi the x. By omit phi, I mean that no tuple in B satisfies every formula in the type. So this up here means no tuple B bar in B satisfies all tuples, all formulas in phi. So for every tuple, there is one formula that makes that is. There is for every tuple in B, there is a formula in psi, in phi, sorry, that is false about it. Okay, so that's the type omitting lemma. So the type omitting lemma in first order logic, for the ones who remember, it's you have a theory T, and then this is the theory T here, the one that corresponds to the theory T. So there is no A in that case. And you have a type that is not principal, so it's not supported. And then you show that there's a structure that satisfies your theory, but omits the type. That's the usual first order type omitting theorem. So here you have your formula, and you have a type that is not sigma alpha supported in A. So the fact that the formulas are pi alpha tells you there is enough to know that it's not sigma alpha supported. And then you need to have this formula phi to be pi alpha plus 1, and then you can make it true. Any questions about this statement? Only why not to take a conjunction of all formula in the type and work with a single formula. That's a good point. The thing is that I guess the type could be uncountable at first. So if you have in that case, we don't want to take a conjunction, because in L omega 1 omega we only take countable conjunctions and disjunctions. So that's why. I mean, I'm kind of doing that when I wrote this here, So that is essentially is equivalent to the type, as you say. But in principle, the type could be uncountable. Actually, it doesn't really matter. At least we're only going to use the countable case. So you are, but then it requires a proof to show that the types that we care are essentially countable, which, yeah, so maybe not to worry about that one. Yes. Another thing to say here is that no, okay. Well, okay, so I'm going to show you how to use it. As I was saying, I'll let you skip the proof. If you really want to, I can give you the proof maybe next time or later today, but I think we're going to spend like a good 45 minutes on this proof. And maybe it's better if you see new things. Just an idea of how the proof goes. For the ones that remember their model theory, the proof in first order logic of the type omitting theorem, one of the proofs is using a hanging construction, which is the same way as you prove completeness in first order logic. And a hanging construction, you have an infinite set of constants, and you start enumerating a set of formulas about these constants, so that they are all consistent along the way. And then in the hanging construction to omit types, you have to make sure that every constant at some way along your construction, you have to make sure that it doesn't, that every constant does not satisfy the type, meaning that every formula, every constant, there is one of the formulas in the type that is false about it. And the reason that the hanging construction works is that because you're only enumerating finitely many constants at each moment, and in this case, you will be enumerating pi alpha formulas, or pi less than alpha formulas, actually. So far, you have only committed to exist to some sigma alpha fact. Exist these constants which satisfy something that is sigma alpha. That's all you committed to, and that since no sigma alpha formula implies the whole type, because the type is not sigma alpha supported, there has to be some tuple in your structure where you satisfy the same things you have committed to, but you can make the type false. So you have to be careful about that. And the way, in general, in first order logic, all you say is that at each step you're consistent. Consistency doesn't work the same way in infinitary logic. You don't have a completeness, or at least you have a completeness, but it's a bit more complicated, the completeness for infinitary logic. So the way you ensure that is that along your construction, you always have a way to map these constants you're adding in your hanging construction to tuples in A in a way that everything is true. You might change your map of how you assign your constant tuple in A, but it has to be always a map where all these formulas are true. Okay, that was very hand wavy. Maybe the only thing to take from it is that it's essentially a hanging construction, but you have to be a bit more careful, and you have to kind of make sure all the quantifiers are correctly. So it's a bit more subtle, but I wouldn't think it's harder. I would say that the only thing that was harder about this type of omitting lemma is to come up with the exact statements, with like pi alpha plus 1, pi alpha, and sigma alpha, so that it works. Like if you don't, like all of this one, and there, if you change them a little bit, it breaks. But once you know that the lemma is true for this combination of these three things, running the proof is kind of, the hanging construction will work. Okay, so let's move on from that, and let's use now this type omitting lemma to prove this theorem. So I'm gonna restate this theorem in a different way. How are we doing in time? We're good. theorem. So consider, so let A be a structure and alpha a countable ordinal. The following are equivalent. Okay, what are the following? One, every polymorphism orbit is sigma alpha definable. Oh. Two, A has a pi alpha plus 1 Scott sentence. And 3, every pi alpha type realized in A is sigma alpha supported. Okay, and then if you look at this, the first one is the one that says that the orbit rank of A is less than or equal to alpha, and this one says that the Scott sentence rank of A is less than or equal to alpha. So that's how you get that those two ranks are the same. And the third one is always one that we need in the middle of the proof. Okay, so is it a good time for a break? No. Let's look at what is easy from here. So 1 implies 2. We did this one already. Done. Let me look it up so you guys can see it. That's that one. If every orbit is sigma alpha definable, then A has a Scott sentence that is pi alpha plus 1. We did it on Tuesday. Okay, so the interesting ones are 3 implies 1 implies 2 implies 3 and 3 implies 1. 3 implies 1, and that's implies. There's a 2 implies 3 because that's the interesting one. And I just sketch 3 implies 1. That's the one that needs a type of meaning there. So how are we gonna do this? So let phi be a pi alpha plus 1 Scott sentence for A. And suppose towards a contradiction, there is a tuple A in A for which the pi alpha type of A in A, and let's put that here, is not sigma alpha supported. Okay, so that suppose 3 is false. That there is a pi alpha type that is not sigma alpha supported. By the way, what do I mean by this? What is this? This is a set of all the formulas. 5x that are, I'm gonna write it like this. They are belong to pi alpha, but I mean they are infinitary pi alpha. All the formulas that are pi alpha and that are true about A. Okay, so by this, I mean the set of all pi alpha formulas true about A. That's the type of A. It's a set of formulas, they're all pi alpha, and I'm taking all the ones that are true about A. So this type is realized. Realized here means that there exists a tuple that makes them all true. So I'm negating 3. So I'm saying there is a type that is realized, but it's not sigma supported. So suppose that's what we have. And now we want to get a contradiction. And the contradiction has to come from assuming that we have a Scott sentence for A, which is 2. What is going to be the contradiction? By the type omitting theorem, there is a structure B such that B models phi and B omits this type, the pi alpha type of A. Right? That's what we get from the type omitting theorem. Because we have a type, it's a pi alpha type, it's not sigma alpha supported in A, and we have this pi alpha plus 1 Scott sentence. So sentence, pi alpha plus 1 sentence, we have a type of pi alpha formulas, not sigma alpha supported. Then there is a B that models phi and omits the type. So that's what we have here. But then if it omits the type, then B cannot be isomorphic to A, because this is a type of A. So this is a tuple in A that satisfies the type, all the formulas in the type. But there is no tuple in B that satisfies all the formulas in the type. So they cannot be isomorphic. Right? And then, but B satisfies this. So this contradicts. So phi cannot be a Scott sentence for A, because it's true about somebody that is not isomorphic to A. Questions up here? Luigi?
We're good.
Cool. Okay, so now we need to look at 3 implies 1. I don't know how much detail I want to do on that one. Let me tell you a little bit about it. Three implies 1. So we know that for every tuple a bar in A to the less than omega, there is a sigma alpha formula. Let's call it phi sub A. That supports the pi alpha type of A in A. So it's a single sigma alpha formula that implies all pi alpha formulas true about A. That's because that's 3. So 3 says every pi alpha type is sigma alpha supported. So whenever we take, so remember the pi alpha type of a tuple is a set of all pi alpha formulas true about the tuple. So this is everything true about A. So we know that for every little tuple A, we can find a formula that is sigma alpha and implies all the pi alpha formulas true about A. So it's quite strong, no? Because it's sigma alpha, but it implies everything that is pi alpha true about A. And the claim is that phi sub A, the formula, phi sub A dx defines the orbit of A. So it's only true of things that are automorphic to A, which is what we need, right? To prove 1, every automorphism orbit is defined by a sigma alpha formula. The claim is that these sigma alpha formula supported types are the ones that define the orbits. So to prove the claim, and there are some little details that are just small technicalities. Okay, so let me tell you the idea. So we consider this set P, which is a set of all the pairs A comma B in A less than omega across A less than omega, such that A models, that such that B models the 8th formula. The formula corresponds to A. And we claim that P has the back and forth property. Which would imply that if phi A is true of B, then AB belongs to P, which would then imply that A is automorphic to B. right? The back and forth property is going to give you this. The proof that it has a back and forth property, I think it's a technicality. It's just something that it requires checking a bunch of little conditions. I don't know if it's rich in the sense that it'll teach you guys much. So I think it's better to skip it if you guys are fine with that. Or that you guys try to do it. Yeah, you can probably figure it out, or maybe you need to read. Or we can look at it if you guys want. Up to you guys. I think the most informative of the directions here is this one. This is like kind of the key point, the one that uses a type committing line. The other one is just that checking that a few things, like the conditions for this back and forth property work, and you have to play around with these formulas a little bit, but there is not much to it. So I think we could skip it. Cool. So if you're fine with that, that finishes the proof of this theorem, and that's how you get that the Scott sentence rank is the same as the orbit rank, which is one of the main theorems that we had at the end of that lecture. All orbit rank is the same as the Scott sentence rank. To continue with this theorem, the fact that the copies this in the are pi alpha in the Borel hierarchy, the same as this is essentially a theorem of Lopez Escobar. What I could do is next class talk a little bit more about this topology. I don't think we can do this proof in the time we have because this requires forcing or variation or some other things that are equivalent to forcing. I guess in Sugao's book is done using the Vot's transforms, which is essentially the same as forcing. And then the equivalence with this one, I think next class I would like to restrict to the case alpha equals 1. I don't know if it's, and the case of continuous functions, which is rank equals 1, essentially atomic functions, and that's the one that is related to computability theory. And mention the connection of continuous functions and computable functions and do all that next class. And for the second part of today, I don't want to go into this exactly this or this, but go and see how is that the back and forth relations are useful to us and see a bit of these back and forth relations. Okay, so after the break, we'll look at that. So, okay, so let's take a 15-minute break that we usually do.
Yes, so we'll still come back at 45.
45, yes. We'll do that.
Do you have questions? Do you have questions? Okay, then we come back at 45.
Cool. Cool. All right, so welcome back, everybody. So now we want to talk about these back and forth relations that I mentioned at the beginning of the talk on Monday. So there was an exercise, for instance, you guys, I guess you guys tried or did on Tuesday, that was to show that the Scott rank of an ordinal omega to the alpha was less than or equal to 2 times alpha. Right, Luigi, did you guys do that?
Yes, I think we did that.
Right.
I think,
So,
yes. I think Sule has write it down.
Okay, so the proof of that one require, I mean, I don't know how you guys did it. There are two ways of doing it. One is to show that every orbit, every element, actually, because it's rigid, every element is sigma to alpha definable. So there's a sigma to alpha formula that defines it uniquely. I guess that was the hint that I gave. So that's probably the way you guys did it. Another one, which is, I guess, almost equivalent, is to show there is a pi 2 alpha plus 1 Scott sentence for it. I guess, yeah, you will have to do that one first. But doing this only gives you an upper bound on the Scott rank, right? You know that is less than or equal this number to alpha. But this doesn't tell you that there are any simpler formulas. It might be a simpler way to define the orbits, right? If you want a Scott rank, you need the least complexity, right? If you think about it, so far we have no tools, or at least what we have talked so far, to prove a lower bound like that. Lower bounds are a bit more complicated. There are two ways to prove lower bounds. One is using back and forth relations, which is the one we're going to mention, which is a more structural way. And the other one is a more comparative theoretic way, which is to prove completeness results or hardness results, like separating certain things is sigma alpha hard, or maybe the descriptive set theoretically show that things are both-phase sigma alpha hard. That will also give you lower bounds. So you have to reduce complete sets into certain things. So let's look at this back and forth relations, which they are a combinatorial tool that are very useful here. So, okay, I need to connect the pencil for a second so it connects. Okay, cool. So back and forth relations. Definition. So we say that a structure, if you're given a structure and a tuple inside the structure, we say that this one is alpha below B. We defined this before, that's why I'm just doing it quickly. So alpha is an ordinal here, so we have a whole set of relations. For each ordinal alpha, we have a relation less than or equal alpha, and they are getting finer and finer and finer. And one is less than or equal to the other one. And then there is a back and forth definition, and it says that for every tuple D in B, there exists a tuple C in A, such that, and okay. For every beta less than alpha, such that A extended by C is greater beta B extended by D. Okay, and as I was saying in the first class, in the case when alpha is a successor ordinal, we don't need to consider all the betas below alpha. It's enough to consider beta alpha minus 1. That will imply all the other cases. So in that case here, we just put alpha minus 1. In the case when alpha is a limit ordinal, we need to consider a sequence converging to alpha. Okay, so this is a way of writing both at the same time. But it might have the intuition to think that in the successor case, the only beta that matters is alpha minus 1. Okay, and then we need to define the zero case, and I'm going to do it different than the first time, now using like the comment that Ruishi made that time, because now we want to go into details. If and only if A and B satisfy the same quantifier-free or atomic formulas among first few many lengths of A many. Okay. Yeah. So those are the back and forth relations. It's good to play a little bit with them. Let me tell you why is that they are interesting first, and then we prove this theorem later. So the theorem that characterizes them and that shows you where they come from is the following. So you have that A is less than or equal alpha B. Sorry. B, and this is for alpha greater than 1, at least 1. If and only if the pi alpha type of A in A is a subset of the pi alpha type of B in B. So in other words, this is the same thing as saying i.e. every pi alpha formula true of A is true of B. That's what it means to say that the type of A is a subset of the type of B. Okay, so I mean, this theorem, I mean, it might look surprising at the beginning because the two things are saying completely different things, right? One is about which formulas are true in A and B, and the other one is a purely combinatorial definition of this back and forth relation, right? But then there you can see how is it they are used, because now we can see what things are true, if there is a way to separate tuples. When is that two tuples or two structures satisfy the same formulas, we can analyze that by analyzing these structures, these combinatorial things. So let's prove it. So before we prove this theorem, let me just mention a few things, a few examples before. I'm having notes here. Let me put it here so I can look at them before my notes. So for instance, I can mention the examples of in linear orderings. They're easy to, more or less easy to understand. So here is an example. Let me call it a lemma because this is actually pretty useful. Lemma for linear orderings. Again, I'm using the example of linear orderings because they are the simplest to play around with in a course like this. A and B, which have first elements. We have that omega to the alpha times A is less than or equal in the back and forth relation alpha plus 1 omega to the alpha times B, if and only if the size of A is more than the size of, it's less than, greater or equal to the size of B. If they are both infinite, they will say that they have the same size, number of elements. If one of them is finite, then that's when this matters. So that's a lemma. It's purely combinatorial. I'm thinking whether it's worth going through the proof. I'm inclining towards not going to the proof. Okay, by the way, so let's look at this a bit more careful. So when you multiply a linear ordering, you guys know how to multiply linear orderings? Have two linear orderings, multiply them, you get a new linear ordering. And the way you do it is you consider a set of pairs from one element and the other. And the way you order them is the one on the right has more power. So you first compare this part, and then if those parts are equal, you compare these parts. It's backwards from the usual intuition that you have, but that's the way people do it with linear orderings as a standard way. I don't know if I should write that on a side so you guys see it. So if you have like in C times D, you have that the pair C comma D is below C comma D prime, C prime comma D prime, if and only if less than or equal. Sorry, less than D is less than D prime, or D equals D prime and C is less than C prime. So you first compare the one on the right and then compare the one. Okay, so for instance, if you say omega the alpha times 2, that means omega to the alpha plus omega to the alpha. Yeah. Cool. Okay. How would you guys go about proving something like this? And again, I'm saying that it's a technical proof that I guess it could show you how these things work, but I think I'd rather do other things. But let's think about it for a little bit. How would you think of proving something like this? Well, you need to do the following. You need to take a tuple from here. That's what it says. From the right-hand side, and find a tuple here, such that you get now the relation on the other way with 2 alpha. Right? That's what this would say. Remember, in the case of successor, we can use the previous one. And of course, a proof like this is going to be by transfinite induction. But then every time you go one step in alpha, this is going by 2 steps. So in the proof, we need to do 2 steps. So we need to first consider a tuple here and find a matching tuple here, and then show that for every extension of that tuple, we can find a tuple here, and then we can use the transfinite recursion. So it's like a 2-step thing to do the recursion. I had to extend and then extend. And every time you extend, you have to find matching tuples from one side to the other. And the tuples that you find are not going to be exactly the same, but they have to be at least satisfy the relations that you want. So you have to play around with that. I would say that we could do an example. For instance, omega times 2, so omega plus omega, is less than or equal 3 omega. Okay, in this case, we have A has 2 elements and B has 2 elements, and alpha equals 1. So A equals 2, B equals 1, alpha equals 1. How will you guys do that? Let's see if we can do this completely. So we have omega plus omega. And here we have omega. And we want to show this less than or equal to 3. Okay, so we're going to start by taking a tuple here. Let's call it B0, B1, B2. And we want to find, want to find a tuple A1, A0, A1, A2, such that omega plus omega with the tuple of A's, with those 3 A's, is greater than or equal to omega with the tuple of B's, right? That's what we want. Okay, so we don't know yet how to do this, but okay, let me tell you how the proof is gonna go, and then because I know where to find them, what we're gonna do is choose A0, A1, and A2 here. Okay, and then I want this interval to be the same, this interval to be the same, and this interval to be the same. These intervals are finite. I'm inside omega. So there are finitely many things here, finitely many things here, and finitely many things here. So I choose exactly the same here and here and here. Okay, so now whenever I choose tuples inside here, I can match exactly on the other side. So below A2 and below B2, these are two finite linear ordinals that are exactly the same. So we can always match them exactly. Right? So now if I want to prove greater than or equal to, I have to worry about this and this, which is the part that are different, essentially. So what's going on now is that we need to show that this part to the right is greater to than this part to the right. Now this part to the right is isomorphic to what? Omega plus omega. And then this part to the left is isomorphic to omega. Right, so essentially we need to show that omega plus omega is greater than or equal to omega. I'm talking about these n tails of things. So that means what are we gonna do now? So now we're gonna take, okay, let me just extend this picture a little bit more. So let's suppose that this omega goes up to here and the other omega goes up to here. So now I want to take a tuple from here, 1, 2, 3. Let's just choose this 1, 2, 1, 2. So this is A0 prime, A1 prime, A2 prime, B2 prime. And now I want to find a tuple on the bottom. So I want to find the B prime on here, such that omega plus omega, and I guess I'm going to use A's, comma A primes, less than or equal 1, omega B's, comma B primes. So maybe I'm choosing some other things in here, but these are isomorphic, so I can always match the things in here and the things in here. There's no issue between matching these guys. The only one that are interesting are the ones in here. And the ones in here, I can match these and these to be equal if I want. But then this one I won't be able to, because I have only one omega. So this is going to be finite. This part is going to be finite, and this part is going to be infinite. And then these ones I can do fine. Whatever, I can choose whatever. So now essentially I'm left with the problematic case is this thing that is finite and this piece up here. But I only need to show less than or equal 1. So it's only one more iteration of this matching thing. And that is going to be fine because now this thing up here is always smaller than this one here. So whenever I choose any number of elements here, I can match in this within here because that's omega, so that they are in the right order. That's all I need because now the next level is equivalence up to 0. So up to 0, I only need them to be in the same order. Okay, so then I match them, and then that's the end of the game. So I can go like back and forth 3 times without losing. Okay, so if you want, you can think of this game as there is 2 players, the one that is trying to match, the one that is trying to match starts by playing a tuple here, and then the other one has no. So the one that is against the opponent picks a tuple here, you find a matching tuple here, and now you have to prove the 2 relation. Now the opponent chooses here, you want to match here, you want to show the 1 relation. Now he chooses here, you want to choose here, and you want to get the 0 relation, meaning in the same order in this case. So it's 3 iterations of this matching game, and you always end up with the same order. You never breaks. So you couldn't go further. You couldn't go to 4, and you couldn't even prove. This is also not the case. So I leave you guys this as an exercise. This is purely combinatorial, just playing with the little numbers to verify that this proof works. This is a picture proof, like it's missing the details. So try to work them out. And try to see why is that we don't get the relation the other way. Okay, so this is the exercise for this afternoon. Once you see that, you're probably going to see, once you're there, how to extend it to this situation, and then how to extend it when alpha is larger, and to prove it by recursion. It's still going to become more apparent. You have to be, I guess, write it down in a very careful way so that everything works in this situation. We can look it up you can look it up in the book if you want. Okay, so maybe a lemma that is useful that I was using here and is useful to prove these things. Let me just write it down as a hint for the exercise. Lemma, you have that for linear orderings A and B, A is less than or equal alpha B. If and suppose that A0 is less than A1. Suppose they are in order, by chance they are in order. If the intervals be AI plus 1 is an interval inside A is less than or equal alpha, the corresponding interval inside B for all I. And of course, when they say interval, I also mean the interval towards infinity on one side and the interval towards infinity on the other side. Okay, so if you have a tuple, for this to be true, like when you have a tuple, essentially you're separating the linear orderings into finitely many intervals, including the ones to the infinity. So saying that this is less than or equal is the same thing as saying that each of the intervals is less than or equal, the corresponding. Okay, so that's a useful lemma that you could use if you're trying to prove this. And that makes the combinatorics of linear ordering a bit easier. Cool. Okay, so let's see what we can do with this. Corollary is that the Scott rank, Scott rank. Let me call it just of omega to the alpha is 2 alpha. So now we get the equality. So we already showed, you guys already showed in the exercise the less than or equal. So let's show this inequality. And we're going to use the Scott sentence. We showed all these ranks are the same. So let's use the Scott sentence rank. So we want to show that omega to the alpha has no pi delta Scott sentence for delta less than 2 alpha. How do we do that? So suppose phi is pi delta, and delta is below alpha. So if delta is below alpha, below 2 alpha, so delta for some beta below alpha, we know that delta is below 2 beta plus 1, correct? So either is equal to the previous one, which will be 2 alpha minus 1, or yeah, right? So delta below 2 alpha implies that for some beta you're below, sorry, less than or equal to a beta plus 1. For some beta strictly below alpha, right? Because this one is below 2 alpha. Okay, but then what do we get? Then omega, what is the connection between omega to the alpha and omega to the beta in terms of the back and forth relations? Omega to the alpha is equal to omega to the beta times omega to the alpha minus beta. This is a property of exponentiation of ordinals. And where alpha minus beta is the ordinal that if you add to beta, then you get alpha. So it's abstraction on the right side, on the side that you have abstraction. And then this is omega to the, and then omega to the beta is the same as omega to the beta times 1. Right, so if this one is our A and this one is our B, we know that A greater than or equal to B. Because B has one element and the other one has infinitely many. Right, so beta is below us. So here we get that what we get from this lemma is that this is less than or equal to beta plus 1. So that means from the lemma that if phi is true of omega to the alpha, then phi is true of omega to the beta. Right, because delta is less than or equal to beta. So in particular, this is 2 beta plus 1. Every 2 beta plus 1 formula true about this one is true about this one. And phi is one of these. So no phi 2 beta plus 1 sentence can be a Scott sentence for omega to the alpha. Because we find that if it's true about omega to the alpha, it's going to be true about a smaller ordinal from omega to the beta. So I can never uniquely identify omega to the alpha. Cool. So that's how you get that you couldn't find a Scott sentence that is smaller rank. So that means that's how you get that Scott rank is actually equal to 12. So and it's a corollary again. So I'll skip the proof, but I'll tell you what the result is. In general, for an ordinal delta, the parameter parameterized Scott rank. I didn't define this, I guess. Of delta is equal to 2 times the logarithm of delta in base omega, where log omega delta is as such that omega to the log omega delta is less than or equal delta is less than omega to the log. So the logarithm is whatever ordinal you have to raise omega to the power of to get close to delta. So between that ordinal and that ordinal plus 1, delta is in between the omega powers. That's the log. Parameterized means that exists parameters that you add to the linear ordering to get the Scott rank. So like in the case of the orbit Scott rank, there exist parameters such that every orbit is sigma alpha definable using those parameters. So you get a very nice calculation of the Scott rank. And in the case we have parameters using this back and forth proofs. Another corollary of the lemma that we had before is that there is no L omega 1 omega sentence whose models are the class of well orderings. So the L omega 1 omega sentences are pretty strong, and we saw that, and you can many things that you couldn't say in first order logic, like being a torsion group or a connected graph. You can say them with L omega 1 omega. So most classes of structures that you bumped into, you can axiomatize in L omega 1 omega. But the class of well orderings is one that you cannot. Kind of the first example that you cannot. So there is no L omega 1 omega sentence axiomatizing the class of all well orderings. It's an old theorem, Lopez Escobar maybe, or somebody. And the proof is that suppose, so let phi be a pi alpha formula true of all well orderings. We claim that in that case, it must also be true of something that is not well ordered. So in particular, is 2 alpha. How do you do that? So consider omega to the alpha plus 1, which is the same as omega to the alpha times omega, and omega to the alpha times 1 plus the rationals by, which is, this is your A and this is your B. They're both infinite, so A equals B. So by the lemma that we had before, this one up here, we get that they are connected, back and forth related, less than or equal to alpha plus 1. Right, and now phi is true of all well orderings, and it's pi alpha, in particular pi alpha 2 alpha plus 1. So phi is true here because it's well ordered, so phi must be true there. Because all this implies that all pi 2 alpha plus 1 sentences true about this are true about this. Then and again, we're using here, let me just repeat what we are using, which I haven't proved yet. This theorem that A is less than or equal alpha B if and only if every pi alpha sentence true about A is true about B. That's what we're using here. Cool. What do you want to do now? I guess I wanted to leave you an exercise. I guess your time is kind of up. Exercise. So in a linear ordering, so consider the relation. Well, okay, so this is the thing. Prove that the relation alpha left limit is pi 2 alpha definable, but no less. But not this, but not sigma 2 alpha defined. And in particular, it's not, it doesn't have a simpler definition. And then what definition is, so 0, I guess it starts at 0. So 0 left limit. So x, this is in linear orderings, in linear orderings. X is 0x limit if and only if it's a limit from the left. Okay. So for every y below x, there exists a z such that y is below z is below x. That's what it means to be a limit from the left. X is one left limit. If and only if it's a limit from the left of things that are limits. It's a limit of limits from the left. For every y below x, there exists a z such that z is a left limit. And y below z below x. And yeah, and then x is an alpha left limit if it is a limit from the left of beta left limits for all beta less than alpha. Okay, that's a relational linear ordering. So you're limit of limits, limit of limit, but I'm just considering always from the left. So the exercise is to show that these relations are pi 2 alpha, but not sigma 2 alpha. Pi 2 alpha, you just need to find the definition, not sigma 2 alpha, you need to use the back and forth relations. Okay, so I think it will take too long to do this proof right now. So I'll leave it for tomorrow. So tomorrow I want to show this theorem that characterizes back and forth relations. That won't take too long. Maybe it'll take half an hour. And then I want to show the other direction of this theorem, that if you are, well, uniformly computably categorical, then you are effectively atomic. So this is the case for rank 1. And then I want to tell you how this kind of extends and why this is a particular case of this thing up here about having an isomorphism function of rank alpha minus 1. So we'll do the proof for case 1, and then I just mention what does it mean? What does this means? But to go up in the hierarchy, we need forcing, which we don't have. Any questions?
Do we have questions? I think we don't have questions yet, so we can collect questions during the review section.
Okay, yes. So yeah, again, if you email me your questions in the morning, well, in the morning anyway, after your review session, so in my morning, I can prepare the answers. Also, if there is any of the things that I said that you like to see proofs of, it's better if you email me, so I can prepare the proofs. whatever you guys, yeah, anything actually, whatever you guys think that you would are interested in, I'm happy to give proofs. Yeah, if not, I'll stick to this plan that I had. But if you have better ideas, that's also good.
Professor Yu, do you have any questions?
I have no question.
Okay, so I think that's it. That's for today's lectures. Let's thank Professor Montomba.
Thank you. See you guys tomorrow.
See you tomorrow.
See you tomorrow.